Hello everyone. So to continue with algorithms, what we're going to do is we're going to do this question. This question actually has most of the concepts that we're going to be applying for the entire topic. So what we have here is consider the pseudocode below. So we have our algorithm, question 1, taking an argument of n, right? Then we say, okay, p is equal to 1. Then we say for I starting at I to n, do p being equal to p times 2, right? So just from this you can say that, okay, p is we're getting whatever p is, and then we're multiplying it by 2. Next, so next here, so just to correct what I had written in the what I had shown you in the when we're going over these things, it's not end 4, it's not end 4. So this was actually my mistake, this was my bad. It's actually next, and what next means is just move to the next iteration. So yeah, just to correct myself on that one. And then we say return p. So return p, what return is a way of saying, okay, our algorithm will more like returning, say we have f of x, right? F of x is equal to x squared plus 1, right? So returning is basically saying this value, right? It's more like saying a is equal to f of 2, right? What we're returning, we're not getting this f of 2, we're actually getting the value that will compute here, which will be 5, right? So basically a will equal 5. So that's what returning is. Returning is basically saying the result of the algorithm, we're able to use it elsewhere outside our algorithm itself, right? So after this is calculated, we can then assign it to something else. So we'll have a question that will actually dive deeper into how to do all of that. But to move on, how are we going to start? So first of all is draw a flowchart for this code below, right? So I'm going to draw this flowchart. So I'm just going to go to a new page. Then so it is, so we're going to start our algorithm, right? So we start our algorithm by with our over there and then say start, right? Okay, we started our algorithm. Now we're going to declare some variables. So we're going to say p and then n. Now since n is coming in from the algorithm, we can just say n. So we're going to declare our box there. Then we're going to say we have our n value there, right? In fact, let's not even declare it. We're going to say p is equal to 1, right? So it's fine, since this is coming in from the algorithm arg list, we can just continue adding it. We're not declaring it within our algorithm, it's coming from elsewhere. Then we're going to say for, right? We're going to say for I starting at 1 to n. So while I, so what this basically means, they're saying while I is less than or equal to n, or I is less than or equal to n, whichever symbol you're used to. But mostly when computers we usually use this symbol. It's the same thing, but this is not a symbol that you can actually type on your keyboard. So to that, right? So we're going to move down and say, now if you remember what I had said in the video on control flow, making a simple flow chart, I had said what we can do is we can actually use a decision box to emulate a for loop, right? So because remember, loops are just running based on a condition. In this case, for the for loop, we're running as long as our value I, in fact I was supposed to say I there, we're running as long as our value I is less than an n, right? So I'm just going to go down there, then quickly just fill that in. Yeah, then I'm going to say I, so I starting at 1, so I is equal to 1. We continue our loop there, so we go downwards. Then we're going to say, so if, this entire thing means if, and then we're going to say I is less than or equal to n being our argument for the list. So we're going to say is less than or equal to n, like that, right? So if this is a yes, right? So I'm just going to put my yes down here. So I'm going to say if this is a yes, what we're going to end up doing is what's in here, right? We're going to do two operations. First of all, we're going to say p should then equal p times 2, and then we're going to say next. Now what next is here is just basically just saying I plus our step. In this case, since we didn't specify a step, I is 1. So for the basic structure of a for loop, it's for, then we have our iterator there is equal to, then we're going to say our lower bounds to our upper bound. Then in here you can put a step, which is how you want to be moving. You're going to say do. But yeah, if we encounter a question about that, we'll actually look into it. But don't get yourself too twisted with all the specifics for now. Yeah, so we have that there. Then now we're going to say, okay, in our processing box, right, in our processing box there, we're going to say p is equal to p times 2 there, right? And then we're going to say I should then equal I plus 1. So let me even just make it stand out from my one. Sorry for my handwriting, but yeah, so this is going to be our I there, right? So I is equal to I plus 1, and then we're just going to move like that there to go back into our decision box, right? Like that. So we're going to say, okay, as long as I is less than n, we're just going to keep on looping. We're going to keep on running round and round and round and round. But then the moment we say no, right? We say no. What do? We first of all return p, right? We're first of all going to have to return p. Then afterwards, we're going to stop. Right. So this is how we move. This is how we're able to move from this piece of pseudocode to a flowchart. So we declare p and I there. Then we say, okay, if p is less than n, we execute this. Then go again, check is p less than n, and slowly but surely we're increasing I plus 1 until it is no longer less than or equal to n. In that case, we say no, return p, and then we stop our algorithm, which is the same thing that's going on here, right? Then now we have b there, right? Now what does b tell us? B is simulate the execution of question 1 for the following values: 0, 3, and 4. So I'm actually just going to simulate for I'll show you how to simulate for 3. I'll simulate for 3, and then you guys can then do 4 on your own, right? So you guys can then do 4 on your own. It's a very similar process. So now the way simulation goes is, this is what we do. First of all, we have to say which variables do we want to keep track of, right? Which variables do we want to keep track of? Well, we have n, right? So we have n there. What else do we need to keep track of? We need to keep track of p. We also need to keep track of I, right? So simulation is where we keep track of everything that's going on within our algorithm. So all the variables and all the operations, we just need to list them out in a systematic way. So if I, then we're going to also list our conditions. So we're moving like this. So n, p, I, then I less than n. So we're going to say I less than equal to n, right? What else? Our operations here, these two operations. So p times 2, then I plus 1. So I'm going to keep track of all these things. Then I'm just going to draw myself a very simple table. So this table is used to actually simulate what's going on inside the algorithm, right? It's used to simulate what's going on inside the algorithm, and I'm going to show you how to do that. So this is how you make most of the tables. This is how we are going to go about making them. So we start off, we said we're going to do the one where we have n being equal to 3, right? So we move step by step. So initially our p is equal to 1, and then I is 1 there, right? I is I less than n, right? Is I less than n? That is true, right? That is true. We can just put a t there. In that case, what we're going to do is that we're going to say p times 2. What's p? 1 times 2. That's just going to give us a 2, right? What's I? I is 1. We're going to say becomes 2 over there, right? Yeah, so assign at 1 there. Then what do we do next? Remember, we're assigning these back to p here, right? We're saying p is equal to that, and then I is equal to that as well. So now what's the new value of p? P becomes 2, I becomes 2. Is I still less than 4, right? Is I still less than n, which is 3? Yes, that is true, right? And then what are we going to do there? Well, what we're going to do there is then we're going to multiply that. We're going to say 4, right? We're going to say 4, and then we're going to say 3, and then just continue with the pattern. So once you just know how to do it, just follow the pattern, then just do the operation. So that goes there 4, that goes there 3. This is true, so what ends up happening here, since this is true, we're going to say that becomes 8, right? Since that becomes 8, this becomes 4. 8, 4. Is this less than 3? No, so that's a false. Meaning none of these operations even end up happening, right? So let me even erase this. So our table actually ends here. So our table ends here in terms of simulation. So our result for this algorithm is what? Is 8, because it's the last value that p is at, because our algorithm ends here, right? It technically ends on this step here, so we just get the values since we assign them back here. Okay, so now that we have that, so you guys can actually go simulate for 4, and then now we have this question: what does the algorithm do, right? What does this algorithm actually do? So what you notice is this question, so we actually have to, it's more of us just having to interpret what this question is doing, right? So we're starting at I, right? So basically we've been given 3 there, and then our answer is 8. Now we look at the values of I here. So what you notice is there's a certain pattern. When I is 1, and this is just something you just have to, you don't have to memorize this. This comes in with your, first of all, your understanding of mathematics and just being able to recognize patterns. What is that? When we have I here, our result is 2. When we have I being equal to 2, our result is 4. When we have I being equal to 3, our result is 8. And if we were to continue here, what is 8 times 2? Here it would have been 16, right? So what pattern do you notice here? Well, for me, the pattern that I notice here is that basically it's just equal to 2 to the power 3, right? In this case, what we're just saying is this algorithm is returning 2 to the power n. I'm going to put that in my white marker. So for our answer C, right? For C, our algorithm returns 2 to the power n. So it returns 2 to the power n. Again, this is something that you just have to be comfortable with, and then just occasionally just having to recognize the patterns of what's happening. So different algorithms, it's not always every algorithm will give you 2 to the power n. Some might say, okay, we're finding the first Fibonacci sequence numbers. Some might say, okay, we're trying to find this, etc., etc. So it's all a matter of what do you want, what question have you been given, right? Then now, for what domain of n does the algorithm work correctly, right? So what domain of n does the algorithm work correctly? Well, if we were to plug in 0 here, which was the actual first question, if we were to plug in 0, what you notice is that this remember, this only works starting from I up to n, right? Now, if n is 0, this won't go anywhere because this goes forward. So what would happen is that this would have just returned p itself, which is this p. To have returned this p over here, which would have been 1. So the answer for this one is 1. The answer for this one is 8, right? Then the answer for this one, you guys will calculate. But then, so what you notice that this works for n. So this works for as long as n is greater than 0, right? Greater than or equal to 0. So for D, That is our answer. N is greater than or equal to 0, because if we put in any value starting at 0, it will always give us a correct answer. And you can actually try that by actually simulating it for 0. What you notice is that I is not less than or equal to 0, so that won't run. And what is P initially? P is initially 1, so we'll just get our result as 1 there. But then what will happen if we put in a negative number? If we put in a negative number, that won't work. Alright? If we put in a negative number, that won't work. If I was to say put in negative 1 here as n, right? If we put in negative 1 as n, that would retain 1, which is not right, because 2 to the power negative 1 is equal to 1 over 2, right? But then by this condition, that would not work. So how can we actually make this work for everything? So equal to 0, which is actually our next question here. Modify question 1 so that it works correctly for all integers. So how do we do this? So how do we actually go about doing this? Well, for this one, we're going to make a few changes to our algorithm, right? Let's say algorithm, just call it Q1 taking in n, right? And now, sorry, we're gonna say P is equal to 1, just like it is in the original question. But then this was, again, algorithms require a bit of thinking, but then we want our algorithm to run correctly. But what you've noticed is that if we say 2 squared, this is just, of course, this is 2 squared. But if we say 2 to the power negative 2, this is just equal to 1 over 2 squared. Same thing, 2 to the power negative 3, this is just equal to 1 over 2 to the power 3, right? So the only thing that's altering anything here is the negative, right? So we're going to actually take use of this fact to not modify a huge chunk of the code. We're just going to add a few things that will help us out, right? So what we're then going to do is say, okay, we're going to say O for the original value of n, right? So it's going to be n. So let me just say this is original value of n, right? Just like this. So O for the original value of n, like that. Okay, so we have that there, right? O is equal to n. O is equal to n. Then now we're going to say is we're going to have an if statement. We're going to say if n is less than 0, then we're just going to say n should then equal n times negative 1. Remember, if the answer is less than 0, we're going to multiply it by negative 1 to get back the original answer, right? Then we're just going to end our if here. But remember, we're storing the original negative value of n. This is going to come into hand. Then what we do in the middle here is we just put in the original code here. So you guys just have to copy this code over here and put it as the original, right? This for if statement here. So we're going to say original if original for loop. So you just have to copy that for loop over there, and then what we then end up saying here is after we copy that, so after our for loop makes all those calculations, then we're just going to say, okay, if our O is also less than 0, right? If our O, this O that we have here, is less than 0, let me call it Q to avoid any confusion. If our Q is less than 0, then what are we going to do? We're going to say P, we're going to say P is equal to 1 over P, like that, right? So if our Q is less than 0, remember the original value of n, if it was negative, this would also be negative. So P that there, then I'm going to say and if, and then we'd return P. Return P, and then finally we end our algorithm. So what this will do is that if we put in a negative number, it will turn n into a positive, run our original if statement normally, and then if n was originally negative, we'd get P being equal to 1 over P, which would just invert it, which would give us the right answer. So this is how you go about with this simple algorithms question.